I want to just write a few more things on board before we go on, because I didn't really prepare any lectures for them. And that was about the theory of hypothesis testing. It is similar to the parameter estimation problem that we have looked at so far. So let's consider that you are interested in testing whether the model contains, the data contains or is consistent with model H1, or it is consistent with a competing model H2. H1 and H2 could be as simple as this is consistent with noise background, and this is consistent with noise plus signal, which is the problem of detection that we are talking about. So even the detection problem can be put in a form of hypothesis testing or Bayesian model selection. So the noise background is one model, noise plus signal is the other model, and we can test for consistency. Alternatively, H1 could represent the general relativistic model that describes our waveform. Or it could be a modified gravity theory from which the waveform comes. Given any pair of such alternative hypotheses, one can check for what model is preferred by asking the question, which of these will have a higher posterior probability? So as we have seen, the posterior probability that model H1 is true given data, in fact, I'm going to ignore all other information that might be available in order to simplify writing, divided by the probability that the data in fact describes the alternative model H2. That's nothing but by Bayes' theorem, the probability that the given data is obtained if hypothesis H1 is true, multiplied by the probability, the prior probability that hypothesis H1 is true, divided by the probability of getting X given that H2 is true, multiplied by the prior probability of H2. You can see in this way of writing, you have lost in the process the evidence that used to appear, which is extremely difficult to compute. That's the advantage. So devoid of the evidence. If you know your hypothesis pretty well, as might happen in the case of a binary correlation signal or pure noise model, these are the two examples that I'm taking, then it's straightforward to compute these things. If you don't know what your waveform is, of course, you have to make some assumption what they are. But even when you know what your signal is, I'm going to come back to this, where you don't really know what your modified theory of gravity is when I look at specific examples. But even when you know what your signal is, in one case, there are no free parameters. The noise model is known completely, and it is characterized by the noise power spectral density and its statistical properties. whether it is Gaussian distributed or a modified Gaussian. There are no free parameters there, and we assume that there are no free parameters. Whereas when we look at the signal model, it does contain some parameters. Parameterized signal model. So when you have these alternative hypotheses, it's therefore important to marginalize over all the signal models, because I don't care which particular signal is present in the data. It could be any one of a class of different signals. As long as one of those signals is present in the data, I'm happy with that. And therefore, I must marginalize to get the full probability, the full likelihood. The likelihood must be integrated over all the unknown parameters of the signal model.
Divide of the evidence part.
You might recall that each of these was divided by probability of x. What I mean is that this doesn't change between these two competing models, H1 and H2. Okay? The probability of x is integrated over all models. In fact, we may not have access to all models. That's one of the difficulties. We are competing, we are asking the question, so P of x in principle, probability of getting x is probability of getting x given a particular model hi multiplied by the probability of the model hi integrated over or summed over all the probabilities. That is the same for both models. And therefore, we don't need to, this is a very difficult quantity to compute, especially when you don't have all the models. And therefore, not having to compute it is a convenient thing. Basically, what we are saying is, I'm not looking for the probability of a particular model, but which of the two models are preferred. In fact, it might turn out that neither of those models is preferred compared to a third model. But I don't know what the third model is. All I am doing is, given two models, you can start with any number of models if you want. You can, pairwise begin to discriminate amongst different models. But the good thing is, this evidence that needs to be computed, and a costly one, is not present in model selection. And we say we select a particular model depending on whether this ratio is large or small. This is just a, I'll come back to marginalizing over the parameters in a minute. Let's just introduce some terminologies. To begin with, this quantity on the left-hand side is called the odds ratio. What are the odds for the two different hypotheses? So it's called the odds ratio. The first of these factors is called the base factor. The first of these ratios is called the base factor, and it is denoted simply B12, which is the probability of getting the data given hypothesis H1 is true, divided by probability of getting the same data if hypothesis H2 is true. So it's the ratio of the likelihoods and that's what is really the key factor in determining what the odds ratio is. because this final factor ratio here, which is called the prior odds ratio, P of H1 divided by P of H2, is often subject to biases. It depends on what we think is the correct theory. We might think that it's more likely to have a signal model than the noise model, or it's more likely for the GR to be correct than the alternative theory. We are going to bias that ratio. So that is not what really should be taken as evidence for this odds ratio. Your computation should be, your likelihood ratio should dominate in order for you to make definitive conclusions or confident conclusions about which model should be preferred. So prior odds ratio should be handled with care. It is questionable. Deductions about models or hypotheses should be made based on the base factor. And you will see this in some of the slides that I'm going to show you later. For a practitioner, a base factor of order 10 it can be negative or positive, by the way. Base factor can be negative or positive. It's measured in logarithmic units. So base factor of order 10 is evidence that model 1 is preferred over 2. You might immediately jump at me and ask me why 10, why not 5, 3, 7. That's just a personal choice. The larger the base factor, the greater is the confidence in a particular model. So that's just about the intuitive feeling about how we decide which model should be preferred. So, as I said, in some cases, the model that you are considering might depend on a number of parameters. So, we should marginalize over nuisance parameters, as they are called. Marginalize is just another word for integration in probability theory. Marginalize is not to consider them to be important. So when you integrate over a bunch of parameters, you don't have any dependence on them. That's the word marginalize is used to directly give a meaning to the action that you're performing. So what is that? So we know that the posterior probability of obtaining a certain parameter lambda given the data and a certain model H is, as usual, given by the Bayes theorem, except that this time I'm going to write the evidence on the left-hand side. And this is, by Bayes theorem, equal to the probability of getting the data given a model and its associated parameters, multiplied by the probability that those associated parameters are have a prior distribution. That's it. So I have moved the evidence to the left-hand side. Now let's integrate both sides. Incidentally, each one of these, we know this is a vector, this is a bunch of parameters, that's a model, this is a vector, the vector, bunch of parameters. If you want to explicitly write that down, that's what they are. So this is just Bayes' theorem repeated. Now integrate both sides with respect to the parameters lambda. Okay, there are some small n number of parameters. So we have P, I'm going to write P of x comma h first, integral over all the parameters. The parameter space could be called some manifold M, parameter space, P of lambda alpha x h multiplied by dn lambda. We're going to integrate over all the parameters on both sides. So that's equal to integral P of x. I'm not including any particular hypothesis. We should repeat it for any hypothesis that we want. P of lambda alpha given h. Okay? All I've done is to integrate both sides with respect to the parameters lambda. Here, on the left-hand side, this doesn't depend on the parameters lambda. It's independent of the model parameters. It's only this which depends on lambda. Therefore, I can take it out of the integral, or in other words, move the integral over here. And then notice that this quantity is actually normalized. The integral, this is the posterior probability of obtaining a lambda given the data. When you integrate it over all the parameters, that must equal 1. The posterior probability density is completely normalized. Therefore, this is equal to 1. So that gives us then the evidence that we were after, P of x given h. Sometimes even this is referred to as evidence. It's really this factor here. It becomes evidence when you expand it in terms of the parameters. Okay, so in different contexts, as you can see, the Bayes theorem can be completely rewritten, right? By shifting the left and the right hand sides. As a result, what was evidence can become likelihood, what was likelihood can become evidence, and vice versa. So sorry about that confusion, but it's really inherent in the literature. Anyway, the quantity that we are after, P of x comma h, can be obtained by just integrating the likelihood multiplied by the prior over the full parameter space. So that is what you would need to replace if your model contains parameters. You're not interested in which particular signal is present, you integrate over all of them. So that's the only additional thing that you would need to do. Okay, even though these things look very abstract, in each of these cases, obtaining these quantities is actually pretty straightforward on a computer. Almost none of them, except in the Gaussian model, none of them are calculable. And when things are Gaussian and you are doing Gaussian operations, everything becomes Gaussian anyway, so it's of almost no use. So you have to resort to calculating these things on a computer. So one bit of information as to how do we calculate likelihood. Let me repeat. the final equation we wrote down yesterday, maybe I'll just mention it there because it's something that you have seen already, but you might keep wondering how am I calculating all these different things. What you're doing is, if you want your likelihood function, which is, let's say, what is the probability of x, that is the data, given that I have a certain signal present in it. Remember, that was just p of x minus h given 0. And that was, and then there was the probability of x given nothing, no signal. And that we already knew as well what that was. It was this ratio that people compute when doing Bayesian analysis, and that was just exponential minus 1/2 of h comma h plus x comma h. The only computation therefore involved is this quantity here, x comma h. And what is that? That's a simple integral or sum. In our algorithm, it's the match filter that we are using, right, to compute this quantity. That's the only thing that is computed. This h comma h is computed once for all. It's the norm of the signal. This is the correlation of the data with a specific template or a waveform model, and that is the heart of the calculation. But it turns out that the calculation is dominated not by computing that likelihood, this scalar product, but actually by the waveform h itself. The waveform h might be a post-Newtonian waveform that Cliff Will has been teaching you last week. I don't know if he talked about IMR. Did he? No? Okay. If it is post-Newtonian, it's trivial. I talked to you about stationary phase approximation. If you then generalize that to higher order post-Newtonian theories, then it's still applicable. The stationary phase approximation is still applicable, and you can work out the waveform very easily. However, if the waveform model that we are interested in is the binary black hole signal, as would be useful in test of general relativity we are going to talk about, it's going to be extremely computationally intensive to compute the waveforms. So our calculations are really dominated by just this one bit. Everything else is actually pretty easy. If you're talking about quasi-normal modes, I could do one of the tests of GR on just my laptop. The quasi-normal modes are simple enough that you could work out the entire evidence for the presence of something by just using, presence of a quasi-normal mode signal used on a laptop. But for the long IMR signal, it just becomes very difficult. Now, the final bit I want to address before I go on to the slides is how to combine multiple observations. I think we can get rid of this. I remember Bala was once visiting Cardiff, and we were thinking about how to improve the tests of post-Newtonian theory using multiple observations. I was too busy, and I must apologize, because by the time we completed the work, Alberto Vecchio and I think John Veach, my own postdoc, had completed the work. And it's pretty neat. Because in the beginning, when you are groping in the dark, you think, oh, it's a very difficult problem. Finally, when it is resolved, it's extremely simple. And cast in Bayesian language, which we didn't do, makes life even more simpler. So how do we define this problem? I mentioned this odd special. It's denoted by the symbol O12, script O. Okay, that's what this is equal to. Now, you notice here that this is asking the question, what's the posterior probability of the model H1 is true given the data? Why should this be only one data set? I can take any number of data sets I want, and I can write an equation at least. So, given a bunch of observational or bunch of events, a bunch of observations, observational data, let's call it x1, x2, xn. What is the probability that model H1 is preferred over model H2? You can write that down. P of H1, this is just a mathematical way of writing it, x1 to xn divided by P of H2 divided by x1, x2, xn. By doing this, I want to show you a very beautiful result that comes out of Bayesian analysis. As usual, apply Bayes' theorem, Bayes' rule. It's almost, Leonid Grishchuk used to make fun of it. Why the hell is it called theorem? Okay, it's almost like a rule, right? So in honor of him, let me call it Bayes' rule. It's not a big deal. Before he looked at what it was, apparently he thought it was a great theorem. It's no great mathematical theorem. It's just a rule that follows from fundamentals of statistics, probabilities. Okay, so just write this back in the way we do, namely probability of getting those data sets, x1, x2, xn. Oh, I'm sorry. Yeah, this is fine. Given that the hypothesis H1 is true, multiplied by the probability that hypothesis H1 is true. Divide that by the probability of getting the same data set, x1, x2, xn. If hypothesis H2 is true, multiply it by the prior probability of H2 is true. You might ask, what's the big deal? Well, now I can simplify the left-hand side, provided each of those probabilities are independent of, each of those observations are independent of each other. There's no reason to think that GW 15914 affected the observation of 151226. Okay. These numbers are going to become very confusing very, very soon. So these data sets are truly independent. There's no reason to think we should be. Therefore, if x1, blah, 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 xn are independent, statistically independent, then this joint probability is just the product of individual probabilities. So we can write that down as quite simply, what's the probability of x1 to xn given h I'll now drop the signal because the subscript, because it's true for both the hypotheses. It is simply the product from n going from 1 to capital N of getting a single data vector given that the hypothesis is true multiplied by, no, that's it. Okay? So we can put that back in over here to rewrite this as the product of n equal to 1 to capital N P of x1 h. I want to write the prior before the product. So I'm going to shift that prior here, h1 divided by the probability of h2, and the same product, except that in one case it's h1, in the other case h2. Did I make a, oh, it's not x1, I'm sorry. It's not x1, it's xn, and there's a product over n. And the same here, this is n. The beauty of the Bayes theorem that I was mentioning is I can write these products separately. Each one of them is an independent one. I can factor this out as n going from 1 to n minus 1 and the remaining one, okay? It's easy for me to do it here. So I'm going to put a bracket around each, and then I'm going to say multiplied by the probability of just the nth one, xn given h1 divided by probability of xn given h2. Not the experts, but somebody who has not looked at it before. Can you tell me what's the big deal? What are we saying? I'm just factoring it out, all the previous n minus observations, combining it with the prior, and writing, this is my new observation, nth gravitational wave observation. What's the big deal? And what's the beauty there? Sorry? Prior, yes. The observations that were made, the n minus observations that were made before, together with this, will constitute my new prior. If you made just one observation, and this, for the second observation, the first observations multiplied by your previous prior becomes the prior, new prior. Okay? But in the end, this factor will become negligible. That's the important thing. So the Bayesian way of thinking about the problem very naturally, in the end, dominates. The observations dominate the prior. We are no more biased after a large number of observations. If I go and look out in the sky and I'm looking for a very faint star, okay, you ask one of your friends to look at it, that person says, oh, I'm not entirely sure that star is really there. But then another person comes, oh, no, it's there. And then when you, okay, for the third person, even without knowing, you might think it's not going to affect the observation. But when you combine all of them, it is going to. You don't have to give the prior information, but it is better to give the prior information. If you tell the person that 100 people have seen the star, 98 seem to think that there is a star out there, what do you think? That's a prior. It's of course going to bias them, But think about the moon. You've got to say 1,000 people saw it, all of them said there is a moon out there. You go and look out there. If you say there is no moon, okay, I mean that's something odd. So it is true that the previous observations can bias what you are observing, but that's in the nature of things. And in fact, repeated observations is all about it. Okay, if I don't understand something, I keep on looking at it again and again and again. Repeated observations. I keep reading. I could not understand what Chris Van Broek wrote in one of his papers, so I had to go back and read it again and again and again. Finally, I understand it. It's like that. Eventually, it will. Of course, you can question the process of observation itself. That is, observing the hypothesis H1. You consider only H1 and H2. Maybe there is a different observation. Maybe it's not the moon out there, a huge spaceship. How do you know? So you could change your paradigm, but the fact that the previous observations play a role in future observations is brought about in this simple equation. Okay? In fact, this is what we did when we tested general, GR models with the second event. The priors that we used came from the first observation plus any flat prior that we used. Normally we say, hey, we really don't know what these priors are. Let's just choose one for both of them. But then these actually will not be one. They will be whatever the previous observation story. Okay, with that, I want to describe nested sampling algorithm a little bit by using Chris Van Broek's slide from previous years. I think it would take much longer to describe it on the board. And then I will give you some examples of how these techniques have been applied for testing general relativity and how they will be used in future for similar work. Should we also bring down the other one? I'll bring it down. Bring it down. The other one? I can do it. Because I don't think I need the, or maybe we can leave it. Just in case we need, just in case we need the blackboard. So let me first start with the parameter estimation problem. I'm deliberately choosing examples directly from the paper in some cases. It's published work, just to show you this published work. So this is the second of the gravitational wave observations that I'm showing here, GW 151226, in which we observed a signal lasting for about 1 second, as opposed to the previous one, which was only 200 milliseconds. In this particular case, it turns out, we can use a flat prior in over some range, but then the algorithm that we use, in fact, I haven't told you the MCMC or the nested sampling algorithms, how actually the calculation goes on to determine the prior, to describe the posterior. But the result of that, I'll have an opportunity to talk about that in a minute. This is the probability distribution that we obtain. What is it saying? It's saying this is the first companion, mass of the first companion, 0 to 50 solar masses, 2 to 12 solar masses for the second companion. It says that the two component masses are poorly determined. These are the 95% confidence intervals, dash regions. Says one of them is from something like 5 to almost 10, and the second one is from 10 to 22. But there seems to be a pattern that's very well determined, and that's the chirp mass. The contour that is described here, or really the equation of this line is equation of chirp mass equal to constant. So that's very well determined. But the problem is, how did we arrive at this particular thing? Because you can see the point that we need to explore is huge. In fact, even bigger than that. We don't pretend that our masses are going to be in this small range here. It has to be much wider. So the likelihood needs to be evaluated, but it starts off on a much larger area. Sorry, I got rid of your WKB. I don't know whether that was something important. Much larger area, and you're supposed to have the likelihood significant only in a small region. How does one accomplish it? And that's only 2 dimensions, by the way. Our problem is a large dimensional problem, typically 15 dimensions if you neglect eccentricity, if you include spins. We somehow control it. We bring it down to something like 10 or 11 dimensional space. It's still extremely large. So given the situation here, it's hopeless to naively put a grid. So it's very tempting, hey, let's just set up a grid and evaluate the likelihood at every point. We'll obviously capture that. That might what one might think. And in fact, before the template placement work that you heard on the first day, people used to think this is the way to actually detect gravitational wave signals and at the same time estimate parameters. I remember giving the first talk on choosing a set of templates to explore the parameter space. People said, this is really not necessary. You can just run your Bayesian simulation. The bank of templates that we use is extremely coarse-grained in the parameter space. Okay, the comparison between 2 templates, the overlap is of the order of 0.95, 0.96. Whereas here, close to this region that you want to explore, the points that you need will be 0.99995. Very, very close spacing is required. If you choose a bank of templates for the detection with that kind of close spacing, you will never finish data analysis of even one chunk of data in 1 year. So that's why template banks were introduced. But when you finally come to parameter estimation, you cannot but explore this full parameter space with very fine gridding. If that fine gridding is needed, we can't, again, that's the reason why parameter estimation takes months of computing time as opposed to a couple of days of computing time for the actual analysis. So how do we then arrive at where to explore this? And that is where a great progress, in fact, this technique, Markov chain Monte Carlo, is a technique that is used to efficiently explore the parameter space so that starting from some arbitrary point, you quickly arrive at where the likelihood is largest. Remember, our goal is simply to determine what the posterior is. To determine what the posterior is, we need the likelihood. Evaluating the likelihood function is expensive. I mentioned that most of our time is really spent on computing that waveform. So we need to quickly get there. Of particular attraction is the so-called Metropolis-Hastings algorithm. And I will mention both of them, but won't have much time to discuss them in detail. Metropolis-Hastings algorithm is one. And this combination of these two is regarded as the greatest progress in computational algorithms in the past century. The 10 greatest. It's one of the 10 greatest. I think we should really write that. Among 10 greatest computing algorithms in the past century. For me, of course, the most favorite is the FFT algorithm. Nothing beats it. We couldn't have any work at all without the FFTs, but this really is, for me, maybe third or fourth algorithm that's extremely useful. So what it does is to set out a rule to explore so that you can quickly arrive at the likelihood and minimize the number of computations. So in a few words, let me just tell you what that Metropolis-Hastings algorithm is. So maybe schematics first. In fact, your parameters, the likelihood function that you might want to explore, this is 2 dimensions, lambda 1, lambda 2. So the ridges of the high probability might look something like this. Okay, imagine that I'm simply drawing the points where the likelihood has ridges like this. Okay, it's like a hill, and these are the ridges. So you might start off at some arbitrary point, then you make a random jump given by a certain algorithm. That's the Metropolis-Hastings algorithm. I'm going to describe it in a minute, more precisely. What you do is you make a proposal. This was your starting point of lambda 1, lambda 2, and you want to go to a new point, lambda 1 prime, or maybe I can call this 1, and this is 2, the second point. That's your new proposal. If the likelihood computed at the new point, maybe you go here, if the likelihood computed at the new point is larger than the previous point, you certainly make a jump. But if the likelihood that you computed at the new point is less than the previous point, whether you make a jump or not is defined by a random rule. In fact, you literally toss a coin and you ask the question, am I going to make the jump or not? If it hits heads, you go there. If it is tails, you simply remain and make a new proposal. And this way, you keep moving, and it turns out that because you're always accepting regions of higher likelihood, eventually you end up somewhere close to, let's say, one of those ridges. The only thing that's going to happen is that you're going to reach your summit. Let's suppose that's the summit, and these are the ridges or the paths towards that, and you will keep on making jumps. Sometimes you may walk away randomly, but you realize then, oh, I'm going down. You keep on coming up, and then finally you reach. You do take random walks sometimes because you allow the alternative, right? Even when the likelihood is small, you have to make a jump. That's because this path may not be straightforward. It may not be, you might come across that you have to go through a valley and then rise up again. So it's no good saying that I will never make a jump to a lower likelihood region. You should make a jump to lower likelihood region with less probability. But you should allow that. But this is one algorithm that has been explored in so many different ways. I really don't even have the counts, how many different algorithms have been come up. But the one that has been most beautiful and useful is the so-called nested sampling algorithm. So let me go through these two in a quick manner. I showed you that result from LIGO observations to tell you what we are up to. We are interested in obtaining that likelihood surface, but it's not easy, so what do we do? I can't find the presentation that explains, enumerates that thing, so I'm going to just write it on the board, and then we can go to nested sampling. So what you do is the following. Although it's called Metropolis algorithm or Metropolis Hastings, they are not the only two. There are other people who have worked on this, by the way. But, sometimes name stuff. So the first step is initialize, which means you choose a bunch of points, lambda alpha 0. Make a proposal, a new proposal. Lambda alpha nu. It is not at lambda alpha 1, it's just lambda alpha nu. Compute the likelihood. Lambda at lambda alpha nu. Let's call this likelihood lambda. This is lambda nu, this is lambda naught. If lambda nu is greater than lambda naught, accept the jump. In other words, lambda alpha 1 becomes lambda alpha nu. If lambda nu is less than or equal to lambda, there are two conditions. 3a not at 3a, I'm sorry. If this is so, choose a random number between 0 and 1. So you're going to simply generate a y belonging to uniform distribution between 0 and 1. And then you can choose the threshold. It could be 0.4, 0.3, whatever you wish. If y is greater than epsilon, which is your threshold, epsilon, which is between 0 and 1, then make the jump. If not, lambda alpha 1 is lambda alpha 0. Lambda alpha 0. In other words, you remain at the same point. And the fourth step is repeat. Go back to step 1. Oh, sorry, step 2. Okay? Those would be your steps, but there are two things that I haven't told you here. One, how do we make a new proposal, lambda alpha? and when do we stop this? Any question? Is there anything that's not legible, for instance? No, it's okay. You make it, this is where you have a lot of freedom to make a proposal. What you could do is, I'm at some point in the parameter space here, I'm going to choose a region that is uniform and uniformly move in that region. Could be that. You could be doomed if these parameters are bad in describing the likelihood. Bad idea. So you need to really study the surface even before you actually know what the surface is. You have to have some idea, is this a good parameterization? So this is where people spend a lot of time. The algorithm itself is extremely trivial. I mean, it may look like a lot of bunch of symbols. No, it's not. It's extremely trivial. It's just, as I said, one computation of a single scalar product. But the problem is all these things. Do I use a square region? Am I going to use a Gaussian region, which is very popular? A Gaussian region in n dimensions. Or do I do something else, namely annealing, making all these surfaces rise up so that I can more quickly move towards the peak? That's where, I mean, the parameterization, make a linear transformation to some other parameters which are more natural in describing the likelihood. This is where most of the time is spent. And the second point is about when to stop. You keep on accumulating the points. After some time, you realize I'm really sampling the likelihood surface very well, but I don't know whether I have exhausted all of them. In the sense, if you go back and look at the marginalized one-dimensional distribution for one of the parameters, lambda 1, let's say, it's a whole range. Let's say lambda min to some lambda max. Ideally, I would like to explore the whole region. And I want to know what exactly is the distribution. Is it something like this? You might get something beautiful like this, but that might really, because you're not completely explored the whole region. It might in reality be something different, something like this. But unless you have explored the full region, you don't have access to that information. So exploring the full region is important. When do we stop? The stopping conditions. And there is no unique prescription. It just comes with experience. Sounds like politics, or, right? But it really is. There are really, and I think in nested sampling algorithm, it's somewhat better, okay? So while, I mean, it's for no bad reason that somebody said statistics, how much, oh no, it's another half an hour. Since I am supposed to also tell you something about how to use these things, I'm going to give you a very overview of what this nested sampling algorithm is. I'm using Chris Vandenbroek's slides with his permission on nested sampling. If possible, I want to use the full slide. That's the nested sampling algorithm introduction. That's the parameter estimation. We want to compute this posterior probability from the likelihood, the prior, and evidence. How am I going to do about it? Well, we will write this in terms of this P of D H comma I. We will write it in terms of the likelihood function multiplied by the prior. You know, it's nothing but that. It's integrated over all parameters. We will separate in two parts. This part we will call the likelihood, and the other part is the weights. I want to quickly get where we want. The basic idea of nested sampling is to compute the evidence by rewriting this in terms of a single variable. The problem you have before is that you are supposed to do n-dimensional integrals. How do you convert an n-dimensional integral to a one-dimensional integral? That is what the secret of this is. What you do is you associate for each, first, you actually sprinkle a bunch of test points all over the parameter space. Now, each of those points in the parameter space can be thought to lie on a contour of equal probability. Namely, let me erase this, use the same diagram, lambda 1, lambda 2. These might be now contours. They may not be simple like this. I mean, there may be some other thing here. And so on. It may be a surface like this. You throw points at random in this to begin with. What happens is when you look at one particular point, that encloses a certain likelihood volume. The likelihood will be the largest at that point. So you can progressively keep going to regions of higher likelihood by rejecting points that have the least likelihood. So let's suppose you start with a certain number of points which are called live points. Actually, I can't really use somebody else's slides, it looks like. So I'm going to just describe to you what the nested sampling algorithm is. So you start with some live points and then compute the likelihood at every one of them. You can picturize that each of those live points is lying on a certain contour. And the region within that contour describes the maximum or the minimum likelihood depending on where you are. So when you start with n data points, you keep n minus 1 that have greater likelihoods than the last data point. You reject it and you make a new proposal for just one point. And that one new proposal is the one that, how do you make the proposal is the difficult one. And that, I think, we are running out of time to describe that, but I hope we can cover it in one of the tutorials. Okay? I think there are experts here, better experts here than me on nested sampling, and hopefully they can describe to it in one of the tutorials. What I then want to do is to close these set of lectures with a presentation on what can we do with all these tools, what have we already done. First, I will describe what we hope to accomplish over the next 3, 5, 10, 20 years. And then I will give you specific examples from the current set of observations. Okay. So if this comes along, where is it? Yeah. I think this introduction I'm going to leave. I think we're really running out of time. Okay. Okay. Can we just turn off that light here? I think we can, right? Main.
Can you stand on the same mic?
Mic?
Yeah. Someone sitting on the control room.
You're seeing what?
Just ask.
Oh. Can you please turn off the lights that are... Hello? In the control room, can you hear me? Okay, all right. All right. It's okay. It's not so important. So one of the mysteries of general relativity are black holes. We don't like them, we love them, but we don't like them. I don't know how to express. Huh? Yeah, I mean, it's bizarre. I mean, these are objects which we have absolutely no clue what they are. We would like to think that they are very sexy, and so we should really talk about them. But if you ask me what black holes are, I really have no clue. But nevertheless, they are very interesting from a physics point of view. If they do exist, finally we have to accept. But someday, somebody will come up with a theory that better describes what happens inside a black hole. For the moment, let's not worry. Let's stay outside and see what they are. But even so, Chandrasekhar described them as the most perfect macroscopic objects. The key point is the most perfect. What he means by that is, just as elementary particles, these are big objects that are described by 2 or 3 numbers and no more. Just as an electron has an electric charge, mass, spin, blah, 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 these are just 3 numbers: mass, spin angular momentum, and electric charge if you are lucky. Most of the time we are unlucky, so there is no charge. We worry about only the mass and spin. Emanuele has been giving you lectures on what are the characteristics of these things. Perturbed black holes emit a spectrum of radiation, not just one frequency, but a multitude of frequencies. And which of those frequencies are excited depends on how the perturbation is caused. If you have coalescence of equal mass binary black holes with no spins, you get a bunch of frequencies, probably very boring, but that's what you get, okay? But if you keep increasing the mass ratio, make one of them small and the other one much bigger than that, and include spins in these black holes, then the spectrum that you get becomes richer and richer. There are higher harmonics, as one would call. So the summary is that you deform black holes. I think there was a laser pointer here. Maybe it's back there. Don't worry, I'll find it. Yeah. Deformed black holes emit these radiation, and that's what we want to detect. But then, not just detecting them, we haven't really, if you ask me about GW150914, we haven't really detected quasi-normal modes. We call them black holes. Why is that? It's because we don't have any alternative model. We do not have smoking gun evidence to say that what we have detected are binary black holes. Because instead of binary black holes, if you put some other exotic objects, they gave you the same INSPIRAL phase. The so-called final ringdown radiation might differ depending on whether the final product is a black hole or something else. But we can't see the ringdown radiation. But what if we could see the ringdown radiation? How do we go about testing it? Say it again.
So in the testing GR paper,
yeah.
called combined ringdown scenario about 7.
Yeah.
So are you saying you cannot see?
7 is, no, it's not even 7. It depends on when you start. If you start immediately after, let's say 5M, then you have 7. If you want to start 10M, and most people would like to start at 20M, then there is really hardly any SNR. 2, 3. We do match filtering. You have to speak a little louder. Yeah.
I didn't understand why the testing GR paper, for example, you don't maximize the SNR
As a function of starting time. Yeah, it was something that was done, but the problem is we have a collaboration where many people are skeptical about, are you going to call that ringdown? It doesn't, So the quasi-normal modes really, the linear quasi-normal modes start maybe 20 m. My point has been that if we start early enough, 5 m, but there is no analytical description of the signals 5 m after that, or 2 m after, right? We don't really. Okay.
There is such an analysis done, but that's what we are getting. Like you see the contours of the quasi-normal mode frequencies after
Correct.
time.
Correct.
Estimated at different starting time.
It's not continuous.
Close to the merger, you
Yeah.
see a bias. Basically, they are not very well described as a
No, but they don't. So the point is that the parameters that you get are significantly different if you start too early. So that would screw up our test completely. If I'm a skeptical and if I'm careful, then I really should be saying we don't have a smoking gun evidence. The reason why we say that these are black holes, I already mentioned one reason, which is that there's no better proposal. The second is that if you take sum total of the whole signal, INSPIRAL, merger, and ringdown, that model comes from solving for binary black holes on a computer. That is the reason why we say that these are binary black holes. I mean, computer or analytical models doesn't matter, but it is something that the sum total of everything is what is consistent with binary black holes. However, we have not done these simulations or model building for other types of objects. How do we know that it is not consistent with something else? That is where we perform tests which are very generic and ask the question whether general relativity is correct, because the black hole nature is what is predicted by a combination of equation of state and general relativity. We cannot answer the question of the nature of these objects, but at least we can ask the question about whether general relativity is true. So that's what I will describe. What can we do? These proposals were made a number of years ago by a bunch of authors. What I will show you here, I didn't even know it was actually operating it. That's good. Maybe you already did this, Emanuele, but in simple terms, a quasi-normal mode is a damped sinusoid. There's a damping constant which depends on, and frequency. They both depend on only the mass and spin of the black hole. This would be let's say, the dominant amplitude, but there are a spectrum of modes that are generated. R is the distance to the black hole, and omega and tau are the mode frequency and damping time, as I mentioned. What can we expect for these frequencies? Did you do this already?
Yes.
Okay. So the typical numbers are for a 10 solar mass black hole, it's about 1.2 kilohertz. That would be the frequency, and it would damp out in half a millisecond. The quality factor, which is 1/2 of tau omega, is of order 2. You have some 2 cycles present in that. And that is the difficulty. We can go back and look at the data if you wish. Look at how quickly the whole thing is falling off. And unless you catch it soon after the peak amplitude, it will be gone. It's exponentially damped. It's of no use. These numbers are really for a non-spinning black hole. If the black hole is spinning with spin parameter 0.9, then the frequency is larger. The black holes, within quotes, that we see have spin amplitudes of 0.7 for the final one, and so these spins are important. So what can we do? The parameter space describing a ringdown signal is given here. The initial mass and mass ratio, the spin, the chi effective, distance, the location of the sky, polarization angle, inclination, some arbitrary phase, and T0. These are the parameters in general relativity. What we do is to alter the parameters from those coming from general relativity to test whether or not general relativity is true. Specifically for the ring down, we introduce additional parameters. Omega Lm are the mode frequencies and tau Lm are the time constants corresponding to L equal to 2 and higher. You start with omega 2 and you introduce a new additional parameter which measures deviation from general relativity by a certain amount, normalized by that amount. Similarly for the time constants. The one that we considered in this paper had 3 proposals. Remember, I was talking about model selection. Your model selection, your model could be that the parameters contain those in general relativity plus delta omega 2. Or it could be, it contains GR and delta omega 3. Or it could be GR and delta tau 2 separately. Or it could be just a bunch of parameters that I'm interested in and not others. So you could then go and compute base factor for each of these models. For instance, B123 GR would be H123, which I didn't write, which includes GR plus all these 3 modifications divided by P of the data given GR is true. So we did this for simulated signals, and we combined them by using what I showed you on how to combine different observations. What is plotted is the logarithm of the base factor as a function of signal to noise ratio for different observations, H1, H2, H3, and so on. If the signal to noise ratio is of order 10, 15, the base factor is not quite enough. As you can, I was telling you I like a base factor of about 10. I would like to put a threshold of 10 before I jump around saying that I have discovered some violation of GR. So if that's the case, then I should be looking at something like below. So to detect any violation of any interest, you should be having high signal to noise ratio event, I would say between 15 and 20. Say it again?
The signals that you put in are GR.
Yeah, it could be GR or non-GR signals, and then we look for,
GR
yeah.
and you try to
Correct.
another hypothesis.
Correct. One, you assume, so your data actually contains one of the signals. It could be non-GR, and then you ask for the other one. So here, this is actually non-GR, I1, I2, I3, IK, divided by GR. If it is subscript, that means GR is the competing model. It's the other way around. GR is the standard model, and these are the competing models. So if it is a single observations, you require, just in the ring down signal, by the way, signal to noise ratios of 15 or 20 or higher. And even for our best event, which might be a gold-plated event, might not be seen for some time, we have signal to noise ratio of a few, 3, 4 in the data. So to get this, it's not going to be easy. So you combine observations. When you combine observations, then the posterior probability density, if GR is true, delta omega 2 will be 0. How strongly can we measure this? Or by looking at how strongly we can measure it, you can understand the power of combining different observations. So this considered a single source, the first one here, and it's a broad distribution. And as you can see, I really don't have much power. Even if signal to noise ratio is about 20, the source is located at something like 20 gigaparsec. I don't have a great observations. By the way, this is for Einstein telescope. I mean, that was the detector that was considered. Otherwise, at 20 gigaparsec, there's no way to have SNR of 20 in advanced LIGO for these quasi-normal modes. Okay, but if you combine 20 observations, you had a question or something?
What are the typical masses, component masses? I just want to know.
let me recall. I think they may be in the region of between 50 to 500 solar masses. Yeah. So these low mass objects again won't give it. Look at what we are doing. We are putting this source at 20 gigaparsec or so. Yes, that's correct. That's correct. It does not contain anything else. In fact, linear quasi-normal modes, late time quasi-normal modes, which means after or equal to 15M in this case. Say it again.
At which frequency you start your ringdown?
At which frequency? That depends on the mass. So you look at the peak amplitude, and then you wait for another 10 to 15M, and then whatever is there remaining is your quasi-normal mode. So this is extremely conservative way of doing it. I think the big progress that we need is to model the post-merger signal very precisely. That's the point I would make, Emanuele. Namely, we don't really understand how to describe it analytically by using methods of quasi-normal black hole perturbation theory. If we can get an analytical handle on it, it will be much easier. And it has to be in the form of black hole perturbation theory, and unique way of describing it. Otherwise, we really won't be able to do it for quite some time. As you can see, Einstein telescope. But Einstein telescope, the single event may not be so good, but when you combine 20 sources, then it peaks. And this goes back to what we were saying earlier. Namely, if you make repeated observations, you will be able to eventually concentrate the probability distribution where you have the real value. Okay, that's about the quasi-normal modes. The second topic, not the other, second, I think I have 3 topics. Oh, we're running pretty late. Huh? No, but it's, you have only 1 hour of lunchtime, so I don't want to take your time. Maybe mention these things quickly. Measuring neutron star equation of state is a big deal. It is matter at supranuclear densities. Not only are astronomers interested in it, also nuclear physicists, because one wants to understand nuclei of very large numbers. You know, so these are generated in the laboratories, but one doesn't understand. I will mention briefly how we characterize the equation of state of neutron stars. If you have neutron star of a certain mass and increase its mass, unlike black holes, neutron stars actually have lower radius. Okay? In the case of black holes, as you keep increasing mass, they grow in size. Neutron stars do the opposite. This is actually also critical for measuring the redshift to neutron star binaries from black hole observations alone. So, how easy is it to modify a neutron star or deform a neutron star is measured by its deformability parameter, lambda, which is the size of the quadrupole deformation that you need to, you make, and what kind of external tidal field it produces by that quadrupole deformation. And you can characterize it by using the Lau number. Lambda is 2/3 Lau number times the radius to the power of 5 in unit c equal to g equal to 1. So this has been studied by a huge number of authors who have tried to address the question whether we can measure tidal deformability in binary neutron star coalescences. How do we do that? Well, in the case of post-Newtonian theory, there are terms that arise at 5th post-Newtonian order that do depend specifically on the shape or the structure of neutron star or the size of the neutron star. And this is opposite to, this doesn't happen at lower post-Newtonian theories, but it accumulates and becomes important very close to merger. So by incorporating these effects, you'll be able to measure it. This has been the work of Del Pozo et al. I think this one particular result is from Agathos et al., where they combine observations. This is the number of observations. As a function of number of observations, one particular parameter called C0 in their paper, which contains information about lambda, they considered 3 different equations of state, and the dashed line here, which you can barely see, corresponds to the chosen equation of state. There it is that, here it is that, and this one is here. And after about 20 or so observations, you begin to discriminate between different equations of state. Obviously, they considered only 3. I mean, if you had looked at if I had spent some time on this plot here, you see there are a plethora of different equations of state. So the situation is not quite at a stage where we can conclusively say we will be able to measure neutron star equation of state in the next 5 to 10 years. However, we haven't explored everything, especially for neutron star equation of state, the post-merger signal has not been used. And when you combine that with the INSPIRAL part, maybe things will become better. I think I really ought to stop. It says another 30 seconds. You can do cosmological parameter measurements. And one of the topics that has been of interest to me is that by using the same tidal deformation, you can actually break the mass redshift degeneracy that occurs in binary coalescences and measure the redshift to binary neutron stars by gravitational wave observations alone. I don't have time, I'll stop this, but I had a bunch of slides and I'll give it to Ajit for use. Okay, thank you very much.